and over and over again. So it's 10 years, no one's getting anywhere with this problem. So one guy, this guy named Paul McCreary, comes along and says, we are solving the wrong problem. The problem we are trying to solve is not human-powered flight. The problem is, how do I build an airplane that I can put back together in 4 or 5 hours? That's the problem we're trying to solve, right? So that was the problem he did solve. That was what they actually set out to do. They said, can we build a plane that we can put back together really, really easily? And they, obviously they built a plane and immediately it crashed. But because they could put it back together so fast, they got to try out new ideas. They often got to try out like different models 4 or 5 times a day. And they ended up solving the problem in about 6 months. Because in that time span, they had done 10 times as many iterations as everyone else had in the previous 10 years, right? And that's, I really I'm actually like not a very smart person, but I move very quickly, and I try lots of things, and I iterate very quickly, and so I learn things faster. And that's like, to me, like fundamental practice of data science stuff, like moving and iterating as fast as you can, all right? And the last thing is sort of a shift in mentality. I feel like a lot of enterprises, at least when it comes to data management, they're sort of stuck in the matrix. They're sort of trapped in this mentality of data scarcity, right? It's like I have a 25 terabyte box, and I have to be very careful about what I put in that box, right? And I can't necessarily like keep tables around for a while because I need to delete them because I have more data coming in, or I can't keep intermediate stages of data around, right? And that's just not true anymore. It's just not true, especially on Hadoop. Hadoop is really about data abundance. A 100-node Hadoop cluster is a petabyte of functional storage. That's nothing. It's 100 nodes, right? There's like 100 commodity servers, not like big fancy GPU running things, right? Just really commodity servers. There's enormous amounts of space to store our data. And that means we can do lots and lots of things we do. Like things that we do now, we can do much differently and much better. So for instance, we want to collect everything, right? Typical data warehousing theory, I figure out what metrics I want to compute. I go gather exactly the data I need to compute those metrics, right? Just those metrics. I do my ETL pipeline. I get everything into my data warehouse. I start asking some questions. And then what happens? Immediately I have new questions that require me going all the way back to the operational systems, getting more data, right? Doing the ETL pipeline, tweaking it, optimizing it, doing it again and again. Just don't do that. Just stop doing that. We have tons and tons of space now. Just gather everything. You're going to have to go get it eventually anyway. All right? Thinking in terms of abundance. Thinking it's not a constraint anymore. All right? Let's talk a little bit about building data products. And first and foremost, if we're going to build a data product, we need to build a data science team. To me, there are a lot of analogies between data science, big data products today, and data warehousing circa 1997, right? Your first data scientist is sort of like your first data warehousing architect. They have the purview of like the entire system, right? You think of now we have data warehousing teams, there's ETL specialties, there's business analyst specialties, and there's a data warehouse architect, right? But if you like imagine back in the day when you had your very first data warehouse, it was probably started out with one person who served all of those roles, right? Who did everything across the stack. Jeff talked about this when he was discussing Facebook's initial data team, right? Everybody did everything, and they only specialized like later on down the line. And that's very much true of data science teams as well. The one kind of key difference between a data science team and a data warehousing team is when we're building data products, we're building a recommendation engine, we're building a search engine, we're building a classifier. Data doesn't just go into the system from the operational store. Like data warehousing, we go one way, right? Operational systems, data warehouse, right? In data science and data products, there's a full life cycle of data. The data actually flows back from Hadoop into the operational system. We deploy a classifier. We deploy a recommendation engine, right? So there has to be skills on the team related to production software deployments, right? It's not okay to just like shove these guys off in the corner. They have to actually be able to push things out again into our existing business processes. That's really, to me, it's a lot of the same skills as your data warehousing team with just that extra piece in there in a lot of ways. All right. Choosing good problems. Choosing good problems is incredibly important. I have a philosophy of data science problems and building data products. You should never build anything exactly once. You should never build a classifier one time. If you have some problem and it's like, okay, let's build a machine learning model or some kind of data product to improve it, right? We have some metric we're trying to optimize. You should never do that exactly once. If you've done it once, something has gone wrong, all right? Either it should be a sufficiently important problem that you want to keep iterating on it and keep getting better at it, and so you're going to do it over and over and over and over again, or you shouldn't do it at all. Does that make sense? This is my belief, right? Do it lots and lots and lots of times, or don't bother. Okay? That's generally a good rule of thumb. All right? Designing the model. Sort of, I feel like there's a lot. This is the machine learning, I would say, aspect of the system, right? This is a Rube Goldberg machine. And to be honest with you, most industrial machine learning algorithms are essentially like very sophisticated Rube Goldberg machines. They have lots of knobs, lots of tuning parameters, right? All kinds of stuff in there. And that's okay, because the point of these systems isn't to do any kind of like massive statistical inference. We're not trying to do anything fancy. We're just trying to optimize some function. We're trying to predict something really well. We're trying to make more money. We're trying to detect fraud. That is the objective, very narrowly, right? Whatever we do, whatever we can do to make, basically to optimize that objective is the right thing for us to do, okay? So there's not that many machine learning algorithms that you really need to know about, to be perfectly honest with you. If you know collaborative filtering for building recommendation systems, if you know naive Bayes models and logistic regression for doing classifiers, and if you understand k-means for clustering, you're in really good shape. You honestly are. There are hundreds, thousands of machine learning models out there. You really don't need to worry about the vast majority of them, right? The data you choose and the features you create to use as inputs to your model are so much more important than the actual algorithm you choose in about 95% of the cases. It's only a very small fraction of people that really need to worry about picking the most optimal machine learning model, and that's only when they've already like exhausted all of their other options, and their data processes are already really good, all that good stuff. Okay. That said, you should always mind the gap between your model and your business. All right. Ad prediction is a great example of this. What does Google do? Google wants to predict click-through rates. We post ads, we want to predict the probability that someone's going to click on them. Right. So you would think that if we created a better click prediction model, Google would make more money. They would optimize their revenue. And that's 100% not true, right? Remember the Rube Goldberg machine. There's a bunch of different complicated systems interacting with each other with like feedback loops and all kinds of like unpredictable interactions. So it is often the case that optimizing a single thing does not actually optimize the global objective function. Facebook friend recommendations is another kind of personal favorite of mine. You guys know Facebook, they do like friend alongside there. You can say, people you recommend. The objective of that product is not to get you to click on friend recommendations. It's to get you to spend more time on Facebook. That's the point. So I don't know what it's like for you guys, at least for me. Facebook seems to mix in attractive members of the opposite sex into my friend recommendation algorithm. I'm just almost certain of that, right? Because the point of it is not purely prediction. The point of it is to get you to spend time. Netflix movie recommendations. The best movie recommendations for Netflix are the ones that get you to subscribe for another month. That is the best recommendation, right? But it's tough to optimize for that. It's tough to like kind of bridge that gap between the model and the business problem. So there's always a gap there of some kind. Okay? If we're doing things the right way, if we're going to solve this problem over and over and over again, we're going to do multiple iterations, we want to make all of those iterations as cheap as possible. We're going to make iterations very cheap. And that means we keep all of our data around. We keep raw data, we keep cleansed data, we keep denormalized data. Like we join all of our data together once for analysis, and we just keep it around. You do this already, right? Everyone like joins all their different, dimension tables and fact tables together, build some big denormalized data object, right? But then you use it as like a temporary table, or maybe you like export it to SAS and then delete it later, right? Because you're thinking in terms of data scarcity. And what I'm saying is you don't have to do that anymore, right? You really can just keep it around, keep it on Hadoop, and then analyze it over and over and over again. All right? So that amortizes the cost of every single iteration. If we're not spending time acquiring data, if we're not spending time joining data, if we've like done all those problems one time and using it over and over and over again to solve lots of different problems, each iteration becomes much cheaper, and thus we can do many more of them.